Dah, nyalain itu.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. So welcome back to the special seminar of Physics, University of Indonesia. So today we would like to hear some talk from our young professors of Department of Physics, Faculty of Mathematics, and Earth Science, University of Indonesia. Prof. Kim, Prof. Dong-Hyun Kim. He will present his research about synchrotron X-ray radiation and its application. And his work is done together with our dean of mathematics and our staff here. So, yes, without further ado, so please I welcome Prof. Kim, and the time is yours. So,
hello, I'm Dong-Hyun Kim. Thank you for the kind introduction. So, I mean, Uri is so special in my mind. So, I'm very, I would say, I feel like home, and I'm very happy to be here, and of course, honored to be here. Thank you for invitation and giving me a chance to present this. What I'm doing is, my research field is magnetism. But I was asked to do some public lecture to the student audience. But I see a lot of professors here, so I feel a lot of pressure.
You know nothing.
Because my recent research was presenting conference, so I thought that might be something interesting for students as well. So I think let's make this topic, the synchrotron X-ray radiation. So yes, I'm doing magnetism research, but I do a lot of characterization. Because I'm an experimentalist, we do surface, we do imaging, we do whatever, computational analysis. And one of the powerful technique is the synchrotron X-ray. So let me introduce the thing. So before going into the details, I'd like to introduce myself. I'm from the city of Cheongju. Cheong means green, and Ju means city. So Cheongju means city of green. And actually, it's green. And it's a very good city. So whenever you develop something, you have to dig the soil, and something cultural, inherited comes out, and then all the development stuff. So anyway, that is another charm of the city. We have a spring season like cherry blossom. We have a summer, and you have the winter and the snow. This is in the fall, we have a university festival. This is the K-pop girl group I came to university festival 2 years ago. But my favorite is S-pop. But they didn't come to our university festival yet, so I'm waiting. Right. Okay. And and this is our university. We have four main campuses. Uh, we are here. This is Seoul, and it's like 1.5 hours away by car. If you take a speed train, it will be taking like 40 minutes. We have it here in Cheongju City. This is the Chungbuk State. And CBNU, which is the Chungbuk National University, is one of the 10 national universities in South Korea. And we're located here in Chungbuk State. And we have a new government capital here, very next to the Cheongju City, similar to Indonesian case. We have a new capital in the Kalimantan area, right? We have a Sejong City, which is here. It's like 25 minutes from our campus or something like that. So now almost 70% of the government is already moved in. It will be completed, no, maybe at least 5 years more. Anyway, this is the main campus, and so yeah, and currently the Department of Physics of CBNU is trying our best to be competitive, right? And we have installed Korea's first quantum computer in our department. This is the 13-bit computer, which is supported on the UK, and it's only operational. Second one is in Yonsei University. How many bits? 13 bits. It will be installed, and it actually installed. We are working on it, and probably it will be open to the public soon, and you can even access on remote if you want. Maybe after some months. And we also got some funds for operation of the computer for 8 years, and we have a GLAM project, which is very important project for the South Korean government. GLAM center, maybe so far 5 or 6 centers are selected, and one of them is located in our university. GLAM is a combinational project for all natural science, not only physics, chemistry, bio, and statistics, and many professors are doing it. We started last year, and will be lasting for 5 years. And we also have a BK training program, which is a supporting program for the graduate students. And the topic of the BK training program is the future semiconductor metrology. So it's about instrumentation and characterization of the semiconductor chain. We have many more projects. So simply speaking, we are trying our best to be competitive, and we have some achievements nowadays. Okay, and this is today's topic, because the second synchrotron will be constructed in the Chengdu city. It's now under construction and will be completed in 4 or 5 years, before 2030. It will be estimated to be completed in 2029. But we don't know. We will delay and delay the construction. So this is just imaginary figure. Now it's only flat. Right? Of course, the basic construction is completed. There is a sewer system, there is a water system, the electronic system is completed, and they are now starting to build up the building. Okay, so because of this, we are launching the new department in our university called the Department of Synchrotron Radiation Science at CBNU, which is open for graduate students only, and will be operated by our Department of Physics. Probably next spring semester, we will be opening this new department. Okay. Now, this is the synchrotron light sources all over the world. And as you can, the red dots are synchrotron sources. As you can see, there are many in United States, there are many in Europe, and there are many in Japan, right? There are a few, especially in Asia. There are only one in South Korea, and 2 or 3 in China, and one in Thailand, one in Singapore, and one in Australia, and one in Brazil. So below the equator, I think the Australia and Brazil are the only country that has light sources of the synchrotron. But anyway, as you can see, it has a bunch of them, right? The good thing for the synchrotron is that it's free. It's free for user. So of course, if you are coming from the industry or company, you have to pay to use. But if you're coming from the university and academia, it's basically free. You just apply for the beam time, and if the beam time is approved, you can go. Of course, you have to support your trip by yourself. But anyway, they don't charge the use of the synchrotron. And as you can see, the most cutting edge country for the synchrotron science is United States, Germany, Japan. And the Korea has only one synchrotron so far, and we are now becoming to be the second one. So that's why it goes. And the information for the synchrotrons can be found in lightsources.org, which is the non-profit organization covering all synchrotron sources all over the world. I captured this page yesterday to be fresh. And yeah, as you can see, it says, according to the website, it says of 183,000 papers is published using the synchrotron source, and 130,000 protein structure has been revealed using the synchrotron, and there are now 8,000 set members by the synchrotron, and there are 26 organizations representing 32 synchrotron sources of the worldwide. So basically, you can click whatever you want, whatever the synchrotron source is, and then you can get the information. Okay? And yeah, for instance, synchrotron near the Indonesia is one is in Singapore and Thailand, but it's small. The good one is in Taiwan. So Taiwan has the two synchrotron source, small one and large one, but they have in the one side. So they operate it like one is TLS and the other is TS. They call it National Synchrotron Radiation Research Center, right? NSRRC. Again, you select the synchrotron source, and you can get the necessary information, and you apply the beam time, go there, do the experiment, get the data, write a paper, and so on and so forth. And if you click some interesting synchrotron source like that, they also provide some latest news like this. So I just captured this image yesterday, and according to them, they say the latest news from this synchrotron is something like that. But as you can see, there are some errors, right? So from my expertise, arrow means a spin, so it's a magnetic something. So I click this, and they said, oh, they saw some magnetic property from chromium to selenium 3, triselenide, I mean, using the RPS technique. RPS is a special technique to see the band using the synchrotron. But anyway, they report the latest news using the synchrotron source, and you can just take some time to survey and explore a beamline that you might be interested in, and you can plan your own experiment. Okay. So yeah, let's go to the history of the synchrotron. I mean, that depends on the case, but to me, the dawn of the synchrotron accelerator is initiated by Thomson, right? As you might know, the Thomson invented cathode ray tube, right? You have an electron gun here, it's an anode, and then cathode anode. You have applied the voltage, and electron is accelerated by voltage, and the energy of the electron volt is transformed into the kinetic energy, right? Which means an acceleration. So in this way, he accelerated the electron and applied the electric field to see the deflection of the trajectory. And that's how he discovered the electron, right? So, and then another good example of the early part, the accelerator technology is this is famous Rutherford alpha particle scattering experiment, right? So he invented alpha particle accelerator, which is like this. I took this figure from the Rutherford paper, which you can get the paper PDF and see this kind of thing. So it looks like this. Idea is, as you might know, there is a metal foil, right? And hit the metal foil with the alpha particle, which is basically helium nucleus, right? And then most of them just go, right? But very few of them is experiencing the strange envelope scattering, which is attributed to the existence of the very concentrated positive thing in the foil, which is known to be nucleus, right? This is how Rutherford discovered the nucleus. So anyway, electron acceleration and alpha particle acceleration would be the start of the accelerator thing. Okay. And you don't need to know, but I want to say that there have been huge efforts in developing accelerator technique. For instance, Ising RF accelerator and Cockcroft working machine and so on and so forth. These things actually, if you set in the synchrotron source. Usually, you are not allowed to get in the synchrotron source, but if we have a special equipment and we walk on the synchrotron source, we can see a lot of this kind of thing inside the synchrotron. So this technique, of course, in the form of the developed way, these techniques are still there inside the accelerator part. The important progress is made by the Lawrence in 1937 for the invention of the cyclotron. So, okay, yeah. He is the Lawrence, Ernest Roland Lawrence. Yeah. His position is special in the United States because, as far as I know, he's one of the best respected scientists in the United States. For instance, there are some national labs, like Green, right? Like Green, the United States has many national labs, like 7 or 8 national labs, and 2 of them was following the Lawrence name. One is Lawrence Berkeley National Lab, and the other Lawrence Livermore National Lab. So Lawrence is very special, very special place in United States science because he was the first scientist who got the Nobel Prize after being educated only in the United States. The elementary school, middle school, high school, universities, he completed everything in United States. Right? Before then, of course, there are many Nobel Prize winners, even in the United States, but they studied in Europe, not in the United States. But he was the first person who did everything, did the cyclotron invention and all the research things in the United States. So that's why the US government names the 2 national labs following the Lawrence. So this is Lawrence Berkeley National Lab. And of course, we have synchrotron here. Right? Okay. And using this synchrotron, so it's isn't only for the Lawrence Berkeley lab space, they discovered 16 new elements. 16 new elements in the periodic table. And probably you might familiar with this part, but we don't care about this part usually. But in this part, you can find some interesting elements like number 103, which is Lawrentium. Obviously following the Lawrence name, right? And number 97 is Berkeley. They just found it in Berkeley, Lawrence Berkeley National Lab. And also we have some California. Yeah, 98, something like that. So many elements are found in Lawrence Berkeley National Lab. And LBL has the Nobel Prize winners, 12 Nobel Prize winners. So, anyway, that was the big success of course, not only the synchrotron guys got the Nobel Prize, but anyway, that was the starting point of the Lawrence Berkeley National Lab. So synchrotron and accelerator played a very important role in setting up the United States science. Yeah. So idea of the cyclotron is very simple. So some people say that this might be the first generation accelerator, right? First generation accelerator. So cyclotron is very simple, as you might learn in the electromagnetism class. You have a charge that is moving with the speed v, right? Charge q, speed v, I mean the velocity, right? So q v is going like this, and it's inside the magnetic field B, right? And then the particle field experience is the Lorentz force, Q V plus B, light-handed tool or something like that. That Lorentz is different from this Lorentz. It's Lorentz and Lorentz is another guy. Anyway, by the Lorentz force, electron was hard particle deflected, not going straight, right, by the magnetic field. So if you put the electron here inside the magnetic field, it will be deflected in this way, resulting in some circular motion, right? People call it a cyclotron motion or loss frequency, blah, 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 but anyway, this is a motion driven by the Lorentz force. Then, idea of the Lorentz is very simple. when the electron is moving with its circular trajectory from the right to the left arm. His idea is, okay, let's apply the electric field in a synchronized way. So, for instance, electron is moving from right to left. That means the positive field, the positive side is that side, and then electron is accelerating. Right? After this acceleration, because of the increased kinetic energy, it will be showing some trajectory of the circular with a larger radius. Right? And then again, when it moves from left to right, the same thing happens, but this time it's opposite polarity. The positive field is this side, so electron that way, right? So in a synchronized way of electron motion, you can accelerate, you can give more kinetic energy to the electron, and then you can take it out again. This is how the cyclotron works. Very simple, right? And this is the first, how to say, test instrumentation done by Lawrence, having the 4.5-inch accelerator. 4.5-inch means something like slightly larger than 10 centimeter. The diameter is like 10 centimeter, and you have some cyclotron pitch inside it. And as you can see, if you do the experiment, you might immediately notice that, oh, this is for the water cooling, and this might be for the vacuum pumping, and there might be some electrodes coming in and coming out. The very simple structure. So he could successfully confirm the working mechanism of the cyclotron of the 4.5 small accelerator cyclotron, and he moved to further to develop build a 60-inch cyclotron. Yes. Right. So this is the photo that was taken in the middle of development of the 60-inch cyclotron. And for now, 60-inch is something like a few meters, right? From the modern standpoint of view, that is very small, tiny instrument, but our synchrotron is kilometers. At the time, this is a huge, giant, let's say, instrument at the time, during the World War II. So, Lawrence, it's kind of, I would say, first moment. Lawrence invited all the scientists from the world to work together here. Right? And if you got picture, you see the Lawrence sitting here, the Oppenheimer, and there are 3 more Nobel Prize winners here. So in this picture, there are 5 Nobel Prize winners. He gathered everyone, and then make it go. He persuaded the government to fund it, and made a cyclotron. And then this is the starting point of the national level of the United States. And this is the moment that the physics, especially experimental physics, is in the arm of the genius. It's now, rather than the individual genius talent, it's a problem of collaboration. A lot of scientists work together, communicate, right? Like they do in now. This was the starting point of that. Okay. So, okay. So in Korea, as I mentioned, we have synchrotron, but exactly speaking, there are 2 synchrotron. One is the circular type, and the other is the linear type. Right? The circular type is the synchrotron. Of course, it's way developed than the cyclotron, but the name itself is different. Yeah, most of the synchrotron has this kind of circular shape, and this was built in 1995, 1995, so 35 years ago. So 35 years ago, I said this is too old, but the set members here paid to hear that this is old because they are upgraded many times. And the getting the beam time here is getting more and more competitive. And that's why we decided to build the second one.
What's the energy of the
Energy is a 3G EV. 3G giga electron volts, the key ones. And the new one in Chongqing is 4G. So
First generation, 3 EV. Fourth generation, 4.
No, the yeah, well, in Japan, the GEV is important, but the GEV is nothing. We can, I mean, GEV is only for the purpose of the scientific application. So low energy like 3 GeV gives you a little bit of subtext ray region. And high GeV gives you hard X-ray region. So I'll talk about it later, but roughly speaking, subtext ray is more focused on the electron energy transition, like oxidation or electron, but the hard X-ray is more focused on the structure of the atom, like SCC or whatever. So that's depending on the requirements for the scientific need. Right. And this was built in 35 years ago. This synchrotron is here. And we have built a new one in the linear type here. It was built 7 or 8 years ago. I was with science commentaries machine. But anyway, this is a fourth generation linear accelerator. And now we are building a new one in Chengdu City, which will be completed in 2029. Because it's a fourth generation thing. I talk about the generation thing, right? Yeah, but before that, the schematic diagram of the conventional synchrotron is like this. So we have E beam, electron beam from the linear accelerator. This rename means linear accelerators. E beam is coming injected in this way. And once it is injected, it will be confined in this ring. Right? So the speed of this electron once is almost like the speed of light, 99.99. I don't know how many nines are there, but almost speed of light. And it is confined in here and stored in this ring. So this is a very big vacuum chamber with UHV, and it rounds and rounds. The thing is, and I will talk about it later, but if you put the strong magnet here, right, the electron moving in almost speed of light will be deflected by the Lorentz force, right? And as you learned in the electromagnetism theory, once the electron charged particle has an acceleration, changes the direction it will accelerate. Once the charged particle has an acceleration, it should emit electromagnetic radiation. Because this speed is so fast, I mean, the energy is so high, to emit electromagnetic wave is falling into the region of X-ray. This is how you get the X-ray. So the thing is, I mean, you have many devices here. Right? Every time you bend the electron bunch, you get the X-ray. We call this as a beamline. So usually, some small synchrotron has a 30 beamline, larger synchrotron has a 60 beamline, or something like that. And a new synchrotron in Chengdu City will be having 45 to 50 beamline. And the funny thing is, I mean, as you learn in the electromagnetism theory, every time you emit the electromagnetic wave, that means you are losing the energy in bunch. Right? If energy is conserved, you can use emit the electromagnetic wave, and your energy level is lower. Right? So maybe 15 years or 20 years ago, there was like a so-called storage ring field, meaning you emit X-ray every time at the beginning, right? So your energy is lower than little by little. And after almost like 8 hours, it doesn't fit to the energy requirement anymore. So this is being stumped, and then new electron bunches coming in. So every 8 hours, we call it a storage ring with field, right? So every 8 hours, we have shut down the storage ring field, so you're gonna have a 30 minutes break. Right? And at the time, there was I would say, strong friendship, emotional, I would say, because most of them are from graduate students, wants to do some experiments. I want to graduate, and then we have to successful in the experiment. But as you might know, 95% of experiment doesn't go as planned. Okay. Most of the experiment doesn't go as planned. It's a failure. So in the storage and refill time, many are gathered, and smoke together, and chat together, break together. But nowadays, that storage and refill is gone because they invented so-called the picking devices inside the storage main. So they call the top-up mode. Energy goes every at the top up. It doesn't lose the energy. So storage and refill time is gone. The romance of the synchrotron is gone. They just do their experiments. They don't talk. Yeah. Anyway, so that's just a joke.
Except maintenance, bro. Except for the maintenance.
Yeah.
Done. Several months, twice a year.
That depends on the synchrotron, but mostly they accept the build time quarterly per year, so the 4 times a year. Some of them get the 2 times a year, but in Pohang, we get the 4 times a year. So for instance, in my case, I require 1 week in my one time. So I spend 7 days in line, 24/7, literally 24/7. So we need to go together as a team at a certain time. I then day shift. Okay, and this is the schematic diagram of each stream line. We have some light source, we have some any X-ray optical things, mirrors, blah blah. Then we have sample field. So E is called the beam line. Okay, and this is the just example of the snapshot of the each beam line. But don't be afraid. It's a complex line, many complex things you don't need to know. Just read the sample. And the beamline scientist will tell you, put the sample here. Nothing just put here. And of course, we need to discuss scientifically, but we don't need to talk about any wiring things. They will take care of it. Okay, I talk about the generation. By the way, if my time is up, please break me anytime. So I talk about the generation thing. I talk about the first generation cyclotron thing. The second generation is so-called the bending magnet. Bending magnet is literally bending the beam path. Right? So electron is coming in with almost speed of light. And then we have a strong magnet, north and south. The field, magnetic field is generated along that side. And you're gonna, with the electron bunch, you feel the Lorentz force, right? So it will be bended. And when it bends, according to the electromagnetic theory by the Maxwell equation, you're gonna have the radiation here. This tangential wave. So it's in a Jackson phase. Calculate everything. Anyway, yeah, this is the bending magnet thing. This is the example of the bending magnet, which was chased from some Korean company. Bending magnet actually looks like this. You have many magnet things here, right? And this is the second generation synchrotron. And the first generation synchrotron is, in other words, we call it as insertion device synchrotron. Insertion means you insert something. So rather than the bending magnet, you insert something like this. This is an example of the insertion device. If you can call this as an undulator. Undulator means this is undulating magnetic field. This is the small but strong magnet here, magnetic field pointing downward. And then you put another magnet, this time magnetic field pointing upward. So alternating wave, or undulating wave, down, up, down, up, down, up. So we match the magnet in the downside here. And now, electron is moving with almost speed of light to that direction. And due to this magnetic field, it will be bending. Right? but you're gonna feel opposite direction of deflection into the opposite magnetic field. So you bend it in this way. So it goes like this, it's wiggling, right? So every time it wiggles, it should emit electromagnetic wave, right? And you put for instance, you can do hundreds alternating magnet. Usually, this undulator is like 1 meter or 3 long. Right here. In other words, you can control the wavelength of the emitted X-ray because every time it wiggles, the X-ray matching with this length will be emitted. Right? In this way, you can tune the energy of the X-ray with specific wavelength. Right? So anyway, so we can every time it wiggle, emit, and the accumulated X-ray will be put in this direction. It's very high brilliance. Okay, so this is the if you put this insertion device inside the synchrotron, and then this is called the third generation. Okay.
What's the direction of the X-ray?
Ah,
If the electrons moving that way, then
yeah. So basically electrons in case of bending magnet, because for the simple, in case of bending magnet, if electron is moving and bending in this way, the electromagnetic wave is emitted to the tangential direction.
right. And so basically the direction of the X-ray is following the
Right.
tangential direction.
Right. Yeah. So here it goes this way, but usually we put another strong band after this undulator to make the beam go that way. And we get this beam to that beam line. Right? In this way. So tangentially we get the beam.
And where do the electrons go after that?
Is that?
Where do the electrons go after that?
Good. Another beam line. Another band magnet. So every single time is like at least.
You never need to bring the electrons back to the original position.
It rotates forever and ever until we shut down the system.
But it's a linear shape.
Ah. This is kind of exaggerated, zoomed in.
All right.
This is like 20 meter, I'm sorry, 2 meter long
Okay.
at most.
Okay.
1 meter long.
Okay.
This way.
Okay.
Synchrotron is like
Yeah, that's a
700
combination
meters.
that will bring back the
Right.
Right.
So exactly speaking, it's like a polygon.
Yeah.
Not the perfect circle. Okay. Now it's time for the fourth generation synchrotron. Fourth generation synchrotron is now built in Cheongju City. Simply speaking, this is the beam profile that is looking into your eye. So I told you that the X-ray radiation is a long tangential wave of the electron motion, right? So I'm looking from this way, the electron coming in this way, right? Cause F undulation or whatever, bending or whatever, if you're going that way, I get beam like this, right? The beam profile is like this. Vertically, it's very well defined. But horizontally, it's like almost 1 millimeter. Right? Vertically, few tens of micrometers, but horizontally, several hundred micrometers, sometimes millimeters. This is the third generation X-ray profile, which you look from directly to your eye. But the fourth generation synchrotron allows you to have the beam profile like this. It's very well defined, not only vertically, but also horizontally. The microbeam. So, imagine that this number of photons is concentrated in this small area of beam size, which means it's much more bright, right? It has a much more brightness, like 2 orders of brightness higher. And how can you make this? It's so-called the multiband achromat. Means conventionally in third generation synchrotron drive the beam with the simple magnet, but we use the multiple magnet and then we put, in this case, 7 magnets here to exactly derive the electron beam. And if you put this multiband, then you can get this kind of beam profile. So this is the new generation. That's why we call this as the fourth generation synchrotron. And this will be built in Seoul City, and many other synchrotron sources are planning to upgrade their current status to be this. It's an argon synchrotron. So this is the fourth generation synchrotron, not related to the energy. It's whatever. Okay. And another fourth generation synchrotron is very interesting one, but I don't want to talk about the details of it roughly speaking. So I mentioned there is an undulator, right? Undulator is made of this alternating magnetic field, undulating magnetic fields, so allowing you the beam once go in this wiggling way. So usually the undulator in the third generation insertion is like 1 meter or 2 meter long, but this time you make a 800 meter long undulator. Very long undulator. What happened? What's happening is very interesting. So whenever the electron beam once is wiggled, it emits the X-ray, right? But the X-ray has the wavelength matching with this length, right? And this X-ray will be interacting with the foregoing electron bunch, right? And then X-ray is emitted when the beam bunch is moving, and then it will be interacting with the X-ray that is emitted before, right? So it is kind of resonant thing. In other words, because it's very strong interaction between electron bunch and electric field of the X-ray emitted, it's possible to have a non-linearity, right? So because of this non-linear interaction, the electron bunch becomes initially it is like this, distributed uniformly, but after this non-linear interaction, we have this kind of concentrated electron bunches. This phenomenon is called microbunching. But anyway, due to this microbunching, it allows you to have very strong X-ray, right? So simply by making very long laser, you can have an X-ray, you can control everything, wavelength, and so on and so forth, strong brightness. And this process of nonlinearity is called the SASE, S-A-S-E. S-A-S-E, we don't know what the SASE is, something like self-amplification, spontaneous emission, which resembles the laser, right? Laser is the light amplifying. SER is a spontaneous emission radiation. LA is a light amplification, right? So SASE, when the SASE, excluding L, SASE, the self-amplification spontaneous emission. Right? So this is laser phenomena. Basically, you get the X-ray laser that is tunable by, undulator. And people call it as free electron laser because in user laser, you need to have a gain medium like film or whatever, right? But here you just have a free electron moving inside the vacuum chamber, right? So we call this a free electron laser. And free electron laser allows you to have a very bright field, light, and it looks like in space. So this circumference of the quantum light is we told the something, but it has almost 200. The world's largest free electron laser is in Stanford. It's under the mountain. I have seen it. Under the mountain, it goes like 3 or 4 kilometers. It's really long. So anyway, this is another type of the synchrotron. But the good thing is that it gives you very strong X-ray. The bad thing is that it's very difficult to get the beam height. I mean, this circular synchrotron allows you to have a 40 or 50 beam line. In each beam line, you can branch it out, so you can have a 100 scientists can do the experiment at the same time. But the free electron laser allows only four, two here and two here. So it's very difficult to get beam line. I only get the beam time once so far. So I don't go
Either says beam down.
beam.
The beam is
At the end. At the end, beam is down. Yes.
so they are not inside.
Yeah. So something like 100 hertz, the 100 times per second, that converge goes and it is down. And some physicists doing high energy physics, particle physics guy, are interested in the dumping process because when it's high energy electron dump, something is happening there, they say. I don't know. Yeah. We are not, I'm not interested in dumping. X-ray thing. So yeah, we have to dump. Dumping well is another good technology. Okay. Now let's talk about the X-ray. So this is the light categorized in terms of wavelength and photon energy. So we have to first find the visible. Visible is here, red to blue, right? And in terms of wavelength, it's several hundreds nanometers. In terms of electron volt, there's a few electron volt range. But the synchrotron radiates mostly X-ray. This is, of course, this region. And we categorize X-ray first for the little bit lower energy and soft X-ray, and then higher energy and hard X-ray. So soft X-ray, for instance, has a wavelength around 1 nanometer and energy around kilo electron volt or below, while the hard X-ray has the wavelength like Armstrong range and the energy of the 10 or more electron volt as range. So if you, I mean, some of the students might have an experience in the XLD, right? If you go to the machine and you get the X-ray diffraction patterns, and there might be some X-ray source, right? And that X-ray is copper K alpha line probably, which is located here. So when you investigate the structure of the material of the powder, and you have to use the hard X-ray. Okay. Just okay. The important range here. This is the extreme ultraviolet EUV. EUV is becoming very important in the semiconductor industry because they want to do the lithography with a proper light source. Before, it was enough for using plain this. They use the water, they use very strange technique to get the nanometer or tens of nanometer lithography. But now they're moving to this range because anyway we need to have a shorter wavelength to have a better resolution in the lithography. Increase the memory density, DRAM, ever. So they're using the EUV light source, and for instance, the synchrotron with 3 GeVs, like Kohan or advanced light source, allows you to have these energy range more. And if you go with the 5 or 8 GeV synchrotron, it allows mostly this part. So that depends on the purpose of the scientific research. And before, for instance, I was in ALS and in the middle of 2000, and then at the time, people from Samsung electronics came to the beam line to check the possibility of using EUV to test their thing. And they tested like, I don't know, 5 years, and then confirmed that EUV is fine to go, and they changed the machine from Netherlands company. But anyway, so these are all possible. Not only the hard X-ray, soft X-ray, UV, sometimes IR is also possible. So this is the strong point of the synchrotron. It produces wide range of the light. Okay. So yeah, there is some concept that you might know when you play with the X-ray. The first one is the absorption edge. Absorption edge is very simple because this is the schematic diagram of the electronic energy shell. Right? You have a nucleus, and you have an electron, which is K shell, L, M shell. Right? K means principal quantum number n is equal to 1, n is equal to 2, and n is equal to 3. For instance, you have an electron here. If you hit this electron with a photon, it is kicked out, right? And then other electron will try to fill in this vacancy, right? It can be jumping from this shell or that shell, whatever, right? So energetic transition happens. So this is the K shell thing, energy, n is equal to 1. And if you have vacancy here, chances of transiting to this is like it can be from this L shell, it can be from M shell, it can be N shell, right? So many possibilities. But this gives you very specific numbers of the K absorption X. And I mean K absorption X is when the electron comes to n is equal to 1 phase. L absorption X is when the electron comes to 2s, and so on and so forth. So for instance, Kx absorption for the carbon is 284 electron volts, and the oxygen is 549, and nitrogen 410. So most of the important bio elements, right? Carbon, nitrogen, oxygen is here. So if you want to do the biasing, you have to tune the photon energy to this region. Okay. And some aluminum, silicon, and tungsten, but in my case, I'm doing magnetism, so magnetic element is here. Iron, nickel, right? In case of iron, it has a KH of 7,000 something electron volt and LH of 707 electron volt. I can tune the photon energy either to KH or LH, investigate the magnetic property of the ions. In the same way, you can tune the energy like 853 electron volts, and then you can selectively see the nickel signal. This is the strong point of the synchrotron experiment. You can tune the photon energy, and I mean the sample might be having many elements, but I can selectively, image it the element specific way. Okay.
Oh, wait.
Yeah.
Okay.
Okay. So another important thing is that the electron bounce in the synchrotron it's relativistic because bounce is moving almost speed of light. Relativistic. The gamma factor or something like that is important. So yeah. And important phenomena in the synchrotron is Doppler effect, right? If the source, light source is the same scale, right? The wavefront will propagating in this way, but the light source, I mean the electron bounce is moving almost with the speed of light, right? And then it emits the wave like this, it's propagating this way, it's moving so fast in this way, so you're gonna have very short wavelengths along this direction. Okay, which means this is X-ray wavelength. So very high energy photon is emitted along that way. So this is again combined with the tangential emission of the electromagnetic wave of the subtle motion. It allows us to have a so-called beamline. Okay. Right. So yeah, you can switch the reference frame, right? From the electron reference frame, you're gonna have this radiation, but the laboratory reference frame that we are in, we're gonna have this kind of radiation. And emittance, opening of these emittance is proportional to the 1/2 gamma. Gamma is the gamma factor and relative theory. So the higher the speed is, the lower is emittance. That's why we accelerate the electrons along the speed of light. We'll have this laser-like propagation of the X-ray. Okay. Okay. Let me compare the brightness of the synchrotron X-ray with the conventional X-ray source. I mean, you go to hospital and you can get an X-ray image, right, of the lung, whatever. And the X-ray source in that case is this one. You can buy it. You can pay. You buy it. And if you see the light profile with respect to the wavelengths of this X-ray tube, we'll have this one. But the light profile in case of synchrotron is like this. The number one, the intensity itself is much brighter. How bright? Comparing the brightness of the X-ray tube, the maximum is in the order of, let's say, 10 to the 7. We got the units. Roughly speaking, fair comparison, 10 to the 7 something. But synchrotron case, in case of free electron radio, it becomes like 10 to the 22. The difference is like 10 to the 15? Yeah, 10 to the 15, which is a big number, right? Considering that the universe has the age of only 10 to 10 years, right? The 10 to the 15 is a huge number. So you can have a really bright light profile when you go to the synchrotron. And another thing is that with respect to the wavelength, we have an X-ray like this. If you use the bending magnet, right? In other words, bending magnet is very simple, primitive. You just make the electron bonds bend, and X-ray will be coming out with this broad spectral range. So you can get not only the X-ray, hard X-ray, soft X-ray, UV, if it's even visible, light is coming out, right? When you use the bending magnet. And if you go with the undulator, you can have a profile like this because, as I mentioned, by controlling the wavelengths of the undulating magnet, you can choose the photon energy. So you can specify which energy is coming out like this. And the free electron laser is basically a very long undulator, so we can have more narrow energy distribution and more brighter thickness. So yeah. Okay. So how many times we don't have?
Well, 20 minutes.
20 minutes. 20 minutes. Okay. Okay, take your time. Okay.
So by the way, I have a question on the previous one. So for what is illustrated there as green, blue, and red, they are all generated by different machines, right?
No, they all generate from the synchrotron. But if it's generated by the bending magnet, energy profile like this, very broad. Because just bending
If we have a synchrotron facility, does the facility consists of several parts, like we may have all those.
I mean, one synchrotron has like 40 beam line. Maybe 20 of them are bending magnet, and 20 of them are undulator or bigger, whatever. No.
Okay. So in every beam line, we can do some further treatment on the how the X-ray propagates further before coming into the the experimental approach.
Yeah, exactly. So if you want to, I mean, what you need is a very exact energy. And then you have to go for undulator. So you just need this energy of light, right? And then you apply for the big time of that undulator and ask them, I need this energy, like 845 electron volt. And then they'll give you 845 units.
So the XRD for determining the structure can also use synchrotron?
Sure. Usually at least 2 or 3 and more beam lines for the XRD. Yeah.
I mean the normal XRD machines that universities usually have a standalone. I mean, it has its own X-ray generator.
Yeah, I mean, mechanism same. XLD is XLD. Break, diffraction.
Only the X-ray source.
Yes. What's brighter? So, for instance, the sample is
I
really.
mean, we can also obtain very specific X-ray wavelength using this technique,
Yeah.
the undulator.
Right. I mean, if you go to the, conventional, I would say, so just an XLD machine, you just buy it, and then they will allow you only couple K alkaline or something like that, the 1.5 angstrom or something like that, it's fixed, right? But if you play with the undulator, you can travel around it. Much brighter. That means for the conventional XLD, you need to have at least this amount of sample powder, right? For this X-ray, this nanoflake is enough to see this structure. So depends on the experiment, of course. And also, good thing for the bending magnet allows you relatively least bright light. But still, this is from the synchrotron. This is much brighter light compared to whatever source. And the good thing for the bending magnet is it allows you to scan the energy. You can do the spectroscopy, the very wide region. Sometimes it's very necessary. So depending on the experimental proposal. Okay, so this is the kind of summary of the radiation profile. I mentioned the bending magnet, right? Bending magnet gives you this light, while I mentioned the undulator. Undulator allows you this light. The opening emittance is much narrower because of this, wiggling motion of the electron. So the profile of the emitted light in terms of brightness versus photon energy for the bending magnet is like this, and for the undulator is like this. The energy is very specified.
Very small. There are two beams. This is frequency.
This one, it was harmonics. Yeah. I mean, I don't know, but usually they get something. I'm a user. I just go to Google matter. And this is I don't want to talk about the detail, but this is regular. Something like an undulator, not a insertion device. Regular is good for broad, let's say, broad emittance, which is used for medical purpose, right? So in case of new synchrotron in Cheongju, the CDNU has a good hospital, then we want to build a medical beam line that is having the source of the regular. So in that case, you can have not only imaging but the therapy. The cancer or I'm not good at it. Some doctors in the hospital are very interested in this kind of regular beam line. So it will be built in the second phase. In the first phase, we are building just 10 beam line. In the second phase, maybe another 10 beam line will be built. And at the time, the regular might be installed. Okay. All right. So summary. Yeah, this is a synchrotron, right? Schematic. Right? It's not circle. It's a polygon, right? And every time it bends, it emits the photon. It has an X-ray range. But depending on the bending method, it will be simple bending magnet, second generation. It will be undulator or regular, third generation. And we could put multiband accromate, many magnets to deal with the microbeam. And this becomes the fourth generation.
And this one is the fourth. This one is the fourth.
This one's nothing. I think this is the schematic. And if you really look at the storage lane, it's made of more frequent band. It is too simplified. Okay, I took this picture from David Atwood textbook. David Atwood is my former boss of boss who wrote the textbook about X-ray optics. So he used this cartoon, but yeah, it's very confusing. Yeah. All right, we can skip it. Okay, skip it. Yeah, we can skip it. Yeah. Because we have a student, I want to talk about this coherence. And coherence is interesting concept, right? I mean, simply speaking, when you have a coherence, you can observe the interference state, right? Right? How can you get coherence? Right. I mean, when you say about the coherence, you need to separate spatial coherence and temporal coherence, right? Spatial coherence means like this. We have a white light source, right? I want to make the coherence line from this white light source, like the sun, white light source, right? It has many, how to say, small light sources, so spatially distributed, right? And it also emits a wide frequency, right? So temporally distributed. And the easiest way of getting the spatial coherence is putting the pinhole, right? So you get the screen and make a pinhole here, and every light after this pinhole is assumed to be originated from this point source, right? So this is how you get the spatial coherence. But with this pinhole, you can put another one here. This one you cannot get the interference. Why? You get the spatial coherence, but you didn't get the temporal coherence, right? And how do you get the temporal? Temporal coherence means the frequency should be the same, the wavelength should be the same. How can you get the wavelength should be the same? You can use the monochromator, or in a primitive way, you can use the color filter, right? So you put the red color filter here. This time you don't have a pinhole, you just put the red color filter, and every light after this red filter is red. So you got temporal coherence because red light is going to be a line, right? Now combining this pinhole and red filter, you get the laser line coherence source. Okay, and this is how you get the coherence. Now, so right? So I told you, roughly speaking, you could either second generation banding magnet beamline or third generation undulating beamline. So banding magnet beamline coherence is very low. Why? Electron bunch is bending everywhere. The spectrally it gives you broad spectral range, and also bending trajectory is leaving a lot of possibility of the light source spatially distributed, right? So to make a long story short, bending magnet is not a good coherent source. But on the other hand, undulator is very close to the coherence. Why? As I mentioned, the undulator by controlling the wavelength of the undulating magnet, you can specify the energy. So in other words, frequency is fixed. So in other words, intrinsically you have a temporal coherence, right? Now, to get the real coherence, only thing that you need is get the pinhole, right? So at the axis of the undulating line, just put the pinhole and you get something like X-ray laser. You can get everything. You can get these kind of diffraction or interference, whatever, right? So if your experiment is requiring this kind of coherency, you need to go to the undulating line. But sometimes, in my case, I'm a magnetism guy, so sometimes I do the magnetic imaging. In magnetic imaging, sometimes I don't need the coherence. I just need the contrast. In that case, I go to the banding magnetism. Okay. Yeah. So this is the example of the synchrotron parameters. like say this is the four representative synchrotron ALS in Berkeley, in Bessin, Berlin, and ESLF in Grenoble, France, and Spring in Japan. The electron energy, actually ALS went up to the 3 GeV, right? Electron energy is something like this. ESLF and Spring 8 giga electron volts. And again, higher the energy is not always good. It has almost nothing to do with energy level. That depends on the experimental proposed. So these are the synchrotron parameters. You can get this thing light source if that was it. Okay, so okay. Yeah, and then let me briefly mention about the X-ray optics, because in X-ray optics something is special. Why? For instance, if you want to make a microscope, right? If you want to build your microscope with a visible light, what you need is lens, right? So you have a condenser lens, an objective lens, and do the refraction thing. And then you get focus, and you can build your microscope. But refraction is based on the refractive index, n, right? So n is depending on, it has a dispersion relation, so it should depend on the wavelength of the light. But then when it goes to the X-ray range, the wavelength is like Armstrong or sub-Armstrong, and the n, refractive index of the most material goes to 1. So you cannot refract, right? So you cannot build the conventional microscope, the X-ray range. So you have to use something like scattering or diffraction, or if it is possible, refraction, right? So this is an example of the reflection. Reflection is very simple. I mean, you put the metallic layer, right? And then beam is in, and the incidence angle, same angle, then reflected. That is good for only good for the visible light. In the X-ray, the thing becomes quite different. So even reflection becomes difficult, right? How can you make the X-ray be reflected, right? If you put the simple metal, right, and maybe reflection efficiency is, I don't know, maybe less than 10% or something. Most of the beams are gone, right? So we will try to build some mirror for the reflection of the X-ray. The one of the success was made by so-called using the multi-layer mirror. So using the multi-layer mirror, using the Bragg condition, whatever, they could use some efficient reflective mirror. But still, the efficiency is not so good. Yeah, the maximum efficiency at this wavelength, this is complex wavelength. The multi-layer mirror is like this, and maximum efficiency only at this wavelength is like 70%, right? So you lose 30% of the light, right? In this way, how many mirrors do you have in the X-ray beam line? Every time you pass the X-ray mirror, you lose 30%. Another explaining you lose everything, right? So that's why you have to investigate the X-ray optics, like reflection. Okay. Yeah, and let me briefly mention that the representative beamline technique. And I mentioned that there are like 40 or 50 beamline, right? But each beamline is not so different from others. Sometimes same technique is used for 2 or 3 duplication. So, and if you categorize some beamline techniques, roughly speaking, you can categorize these 4. One is imaging beamline, in other words, microscope beamline. 2, diffraction or scattering beamline, right? And 3 is the spectroscopy beamline, which should be energy to get the spectrum. And the 4th is dynamics beamline. You want to see some physical quantity that is changing with respect to time, right? Of course, this is not totally exclusive. Sometimes you can do some imaging and spectroscopy at the same time, or you can do the imaging and dynamics, or you can do the spectroscopy. And you can combine this technique. But for convenience, you can categorize the beamline technique in four. So before you plan the trip and apply the beam time to the synchrotron, you have to, let's say, uh, you have to specify what we're going to do in terms of this beamline technique. Okay?
So can I go back to the previous slide when you said something about X-ray mirror? I missed the explanation about that before. So what sort of surface that can we collect X-ray?
Surface.
Yeah. How do we reflect X-ray? With visible light, it's easily understandable.
So the visible light, right? I mean, we can explain the reflection by the force oscillation of the
using metal, right?
Right.
So what about X?
That effect is also here, but not that high. In X-ray range, that effect of the reflection also exists, but not that high. What is important is also using the Bragg condition. So simply speaking, most of the X-ray optics is based on the diffraction. Even reflection is using the diffraction. And the lens is also using diffraction.
Price of love loss.
Yeah. That's why we have it's 50 or something. Multi-layer diffraction. Yeah, diffraction is mostly used to. So let me start. Maybe this might be the last one. I want to focus on one technique, the microscope. So I googled the history of the microscope, and they figured out that there was some contradiction. Who invented microscope first? Right? This is one of them who claimed that he invented the microscope first. Janssen, I think it's Dutch, no? And then some development was made by Hooke. This as a physicist, you know who did it, right? Spring also. And he made something like this, and Galileo was made and invented his own microscope, a composite microscope. In 1850, Abbe, first built this composite microscope, which is almost like a modern form of
telescope. Your telescope.
He made, according to the Wikipedia, he made a telescope and a microscope. Okay, and for instance, from my point of view, I'm doing magnetism research. There are so many microscopes, and the question is what to use, right? So microscope has the resolution. Resolution is again like a coherence. Resolution is again having the spatial resolution and temporal resolution. Right? Spatial resolution is like this. The micro resolution and nano resolution. And temporal resolution is like this. So the conventional light microscope has the spatial resolution of the micrometer, and you just use your bare eye. Right? The temporal resolution might be somewhere here. But the X-ray microscope is something like here. It's very strong because X-ray itself allows you to have a good spatial resolution. Not the best, of course. The best resolution is by TMK. But it gives you decent spatial resolution. But at the same time, it also gives you good temporal resolution. Right? Of course, best temporal resolution can be done by some microscope combined with the femtosecond measure. But anyway, X-ray microscope is a good compromise. The good spatial resolution and good temporal resolution. So, yeah. And yeah, comparing the electron microscope and X-ray microscope, this is electron microscope thing. you can use it. Yeah, the X-ray microscope, you can use it, but the lens technique is quite different, of course. In electromagnetic, I'm sorry, electron microscope, you use the electric lens and magnetic lens. While the X-ray microscope, you use this kind of thing. This we call it as a dome plate, and this is an example of the diffraction lens. So this is how you get the diffraction. So, right. To make a long story short, this is how you get lensing using the diffraction, right? Right. Basically, you have a zone like this. This is locked. This is open. This is locked. And this is open. Right. And then every time you open, basically, if you see a cross line, you have a slit-like structure over here. It's a slab, or there's a light source, and then you can have a difference between ray tracing. You get the phase intensity at its position. And you are interested in the central part here. The idea is like you get all the beam diffracted from each screen. You get the beam, and if this is constructive, then you can be working as a lens, right? So mathematically speaking, if you have just a simple circular aperture, you get the line source, coherent line source, you get simple circular aperture. If you diffract it, you get the zones. It is so-called array pattern. You learn in optics. So it's like a Fourier transform. And you have a software thing. If you do the Fourier transform, you get the ring here. And inversely, you put the ring here, and you get the circular aperture. Mathematically, it's the same thing. Anyway, so this is how you get the X-ray lens using the diffraction. Right, and this is the electron microscope snapshot of the zone. So very nice zones. And he made this and he retired. He's playing his winery nowadays. Anyway, he is very happy to put the dust here. And the reality. Anyway, okay. And using the zone plate, you can build up the microscope. And let's take a look at the center one first. This is the analogy of the optical microscope thing. Right? Now, you have the light source, X-ray. You have the sample. And you're going to have this as the condenser lens for illumination, right? And you're going to have the objective lens for resolving the image. This is the transmission of the microscope thing. Instead of the visible light, you're using the X-ray, so we cannot use the refractive lens here. Rather, we have to use the diffraction lens, which is zone plate. So you put the condenser zone plate here and illuminating the sample, and objective lens as a micro zone plate here, and you'll see the image. This is the schematic diagram of the X-ray microscope. The wavelength, I mean the resolution, you're interested in the spatial resolution, right? The smaller the better, right? The X-ray itself is a very small wavelength number, like 1.5 nanometer or so. But we cannot go down to that level because of the imperfection in the optics, right? The resolution is rather limited by the functionality of this zone, right? For instance, mathematically, resolution is limited by the width of the outermost zone. So if you have, the zone has a mathematical pattern, right? The outermost zone width is like 20 nanometer, and then resolution becomes 10 nanometer, nothing like that. So you can buy the X-ray lens, and good lens is like 20,000 US dollars. Bad one, below 10,000 US dollars. So I'm trying to make this one for hobby. because we have a very good EBD methodology. So I'm testing and trying to make this one, and maybe I can make a company to sell it. Good. Anyway, yeah, this is the right, exactly matching optical microscope, an X-ray microscope version of the microscope. And this is something similar, a little bit different because it's a transmission X-ray microscope. This is scanning transmission microscope. So here you have only one lens, right? And then you scan that. So this is how you get the scanning image. And this is also some half electron and half X-ray microscope. This is a photoemission electron microscope. You know the photoemission, photoelectric effect. Sample, take the sample with a photon, and that photoelectron comes out. Right? By analyzing this photoelectron, you can see what's going on here. So this is the example of the photoelectron microscope. Most of the synchrotron has this and this, and some of them has this. Okay. Right. Maybe you can skip it. Yeah, this is what photoelectron microscope. We skip it. It's a bit technical, but just to mention, there are two kinds of microscope, optical microscope. One is a full field. Full field means you're illuminating the light to the whole area of the sample and get the images. While you have the scanning type, you have a micro-sized focus field, and then you scan the sample or scan the light, ratchet scan again, and then you can get the image. So, I mean, it has a long story, but simply speaking, you have to consider which one is suitable for you. Okay. Yeah. So that's the end.
Yeah. Yeah.
Thank you very much, Prof. for the presentation. Is there any question from the audience? Okay. Budi? Thank you for giving a nice lecture today. Yeah. I'm very happy since I can meet you again. Since we met you in CDNU and in Vietnam and also in San Francisco. Yeah. So it is our pleasure to hear that the Synchrotron will build. Yeah. Or now it is built. Yeah. It's built.
On the construction.
Oh, on the construction. Okay. Great. I think it is very important if we can use the synchrotron. So I want to ask what kind of equipment will be located in your synchrotron. Since last month, I brought my student to go to the LSRI in what is it? In Thailand. Yeah. So if I can get information, what kind of machine, for example, exam, SAS, or and another equipment is very useful information. Thank you. Okay.
The question is about what kind of beamline do we have? Yeah, as I mentioned, because of the funding limit, every phase will be going with the 10 beamline this time. The first 10 beamline is fixed. And for instance, X-subs will be there, the SACs. There will be two SACs beamline. And there is, I mentioned this scanning transmission X-ray beamline, we're going to have it. And spectroscopy also, protein crystallography beamline, we're going to have two. So 10 beamline will be available, but most of them is quite general. So, I mean, except James, whatever, it's doable, and so on and so forth. But personally, I'm a little bit disappointed by the government decision to make build the first 10 beamline with no ambition. I mean, it's so general. Of course, we have a very good beam. Brilliance is very high, coherence is very high, and so the experiment time will be dramatically reduced. Like if it took like 10 hours, then it will take like 2 or 3 hours, something like that. But actually, the history is Korean government built another accelerator with the heavy ion collider. It's a different project, but the heavy ion collider project had many problems. The head was fired maybe 3 or 4 times, and it didn't go up to the level as planned. It is operating, but it didn't go well. So the Korean government, Minister of Science, was very afraid that the second synchrotron will be having the same problem. They decided to build the first 10 beamline with the general one. So user-wise, I think it's good. It's general accepts, general sucks, general X-ray microscope will be there with much better beam. So yeah, you can do it. One ambitious beamline is the nano IRPS. IRPS angle result potential allows you to see the band structure very clearly, right? But this one is nanobeam. Multi-band FMS allows a nanobeam. So nanobeam IRPS beamline will be built in the first phase. That is most advanced ones.
When the machine can be operated?
Supposed to be 2029, but
Okay.
so it's not like
Any other questions? Thank you, Professor Kim, for the lecture. You explained about the second generation, third generation, and fourth generation, and how to control the wavelength. I'm just curious how they choke the light so it becomes a pulse light in the beamline. Thank you.
okay. The question is I mean, X-ray is coming out in the form of the pulse, right? Pulse.
Yes.
When you inject the electron bunch to the storage ring, it's already made pulsed. So, for instance, most of the third generation synchrotron operates in the 500 megahertz. So 500 megahertz every, how to say, every 1 second, you're gonna have a 500 mega, 500 times 10 to the 6 bunch. So it's already concentrated by bunch form. So every small bunch is passing through the bending magnet or undulator. It will be emitting X-ray that is matching with this bunch length. And this bunch length is converted to the time scale effect of 50 picoseconds. So it's intrinsically emitting the X-ray pulse with a 50 picosecond.
Is there any other question?
Okay.
Okay, we'll read some of the question. Bagaimana yang pertama nih?
Ini studi kasus yang bawah.
Okay, so this question from Anin Nabail Ali. Okay. Thank you, Prof, for this insightful lecture.
The first question is for the X-ray free electron laser. If you make it longer, then beam becomes brighter. In principle, yes, but in practice, I don't know. In case of Pohang lasers, I mean, there are, as far as I know, there are only four free electron lasers that operational in the world now. In case of Pohang light source, when we decided to make a 800-meter undulator, I mean, in Stanford, they have a 2,000 or 3,000 meter undulator, right? But the beam, actually, the produced beam profile was not exactly proportional to the length of the undulator. So that's why they, as far as I know, that's why they, compromised to the length of the 800-meter in case of Pohang. So for the first question, I think in theory, if you make a longer, if you make bigger, the beam might be brighter, but in practice, there is some compromise point. Yeah, it should be like around 1 kilometer. And the second question is energy of the electron beam generated by synchrotron is not of GeV, but the wavelength of the utilized rays is typically yeah. So right. So GeV energy is the energy of the electron bunch that is orbiting inside the storage ring. And it keeps most of energy, right? Because it's moving, right? So for instance, 3 GeV energy electron bunch is orbiting, right? Constantly. And whenever it experiences a slight deflection of the trajectory, it emits the energy with this level, kilo electron volt, right? So from the electron bunch side, originally it has like giga electron volt energy, and it lost kilo electron volt energy, which is very fractional, right? So it can be sustained in this way. So excessive energy is still carried by the electron bunch orbiting in the synchrotron. And the third question is, how do you usually power synchrotron? Does the beam generator operate every day? This is about beam physics, but I'm not a good expert in the beam physics. What I can say is like this. Yes, it's daily operated. And okay, how about saying this? The electronics bill from the synchrotron, electric bill per year from the synchrotron is like about 10 million US dollars. But considering the factory, like factory pays much more, right? Factory pays much more, but the synchrotron with this big facility only pays just 10 million, slightly less than 10 million US dollar, means it's manageable.
Is it funded solely by the government?
Because first, initially, it was funded by the private company POSCO, the steel company. They built everything, and then they donated all the machine to the government. So now it's operated by the government.
Okay, is there any other question?
The bottom
The next one, the bottom.
I currently work at the company that uses Betatron range. Okay, and my question is, what is the maximum observed dose limit of synchrotron compared to the Betatron? Betatron, I cannot answer this because I don't have any experience of Betatron. What I know is that when I worked at the Orange Bucket National Lab, they disregarded the Betatron.
yang di atasnya Nabil ada.
They
Studi
usually building, and I have never seen in Beratron after that, so I don't know about Beratron. Sorry for not answering. Yeah. Sorry, I don't know.
Is there any other question?
I was wondering about the type of research or the research problems that we can do by utilizing synchrotron, for the magnetic problems. And to my understanding, if you want to probe the dynamics of the spins, we usually need something that carry spins also, right? Like neutron. Therefore, as with the synchrotron, so what sort of magnetic problems usually we can explore using synchrotron?
That's very important and good question. Thank you for that question. Simple answer is that synchrotron is a very, very good and powerful technique for the magnetism research. The chemistry is really good. And for instance, the mechanism of the magnetic, research, magnetic contrast is very well established. One of the examples is so-called XMCD, X-ray magnetic circular dipolarism, right? For instance, you have you have some magnetic material, and then magnetic material means it has a magnetic moment, right? Somehow, and then it has some, how to say, symmetric breaking of this and that, right? And because of that, if you illuminate the magnetic sample with the right circular X-ray polarized light or left circular X-ray polarized light, the transmission and absorption become different depending on the magnetic state of the material. And the contrast is really huge compared to the other magnetic characterizing tool. So, for instance, XMCD can be very powerful tool, and it's very well established. For instance, in magnetism research, our recent trend is to say, there is a magnetic moment contributed from the electron spin and orbit. So there is an orbital moment and electrical spin moment, right? And if you use the synchrotron XMCD, then you can exactly separate the contribution. You can quantify how much spin moment is there and how much orbital moment there, or something like that.
So maybe XMCD.
Very strong. So we're gonna have an XMCD beam line as well in Chongju, synchrotron in the first phase, beam line phase. Yeah.
So you transform to the unpolarized X-ray right circularly polarized or left. So you do it in the special workstation for
so circular polarization of the X-ray can be generated very easily. So in case of undulator, controlling the distance, relative distance of the magnet and array thing, you can tune not only the wavelength, but also the phase. You can control the phase. That means you can generate whatever polarization of the X-ray. So undulator, easy to generate the circular, linear, elliptical, whatever polarization. And even for the bending magnetic beam line, and it's also very established. Our team actually developed a way. Bending magnetic beam line, electron bunch is going that way, and bend it, right? And then X-ray will coming that way, right? And according to the electromagnetic theory, from this orbital plane, radiated electromagnetic wave over and down as an opposite circular polarization. Right. So you can, for instance, put some slit on that upper range or bottom range. You can selectively control and take the polarization, even in case of abandonment. So there are well established.
Okay. So in terms of how XMCD research is done, to my understanding, so using this element specific excitation, right? So we look at certain element, we observe whether the ion, let's say, is magnetized or not using this excitation.
Yeah, that's what I'm doing for 20 years.
Okay. So then what is the the difference in the feature? I mean, so what distinguishes the, I mean, if you compare between XMCD and neutron scattering, for instance?
Neutron scattering, yeah, neutron scattering is a good source, especially good for investigating, for instance, antiferromagnets. Antiferromagnet, I mean, alternating spins at the net zero magnetic moment makes very difficult for magnetic characterization. For instance, antiferromagnet XMCD 0. You cannot see. So you have to see the antiferromagnet using the synchrotron. You have to go to the second order.
So you mean, is it because the same elements can have two opposite
Right. Yeah. So antiferromagnet difficult for the synchrotron, but to be possible, for instance, if you use some special technique like XMLD, the second order effect of the XMLD. But if you go to the neutron scattering, you can have an access to the ordering of the antiferromagnetic spin structure. That's a good thing. I mean, synchrotron is not, all power machine. It's very good and straightforward, but sometimes it requires supplementation. The neutron scattering, very good for antiferromagnetic. Yeah.
Thank you very much.
Okay, is there any other question online? No. Yeah. Okay, thank you very much for your nice presentation. So, yeah, I just want to know which matching. Do you have recommendation which matching can detect spin dynamics with high energy resolution? Spin dynamics like spin wave. Can I detect spin wave?
Yeah, there is some. I didn't try with the synchrotron, but there is a try from other groups to see the for instance FMR, yeah, ferromagnetic resonance signal. Some group try to observe the ferromagnetic resonance signal together with the XMCD technique. They could see something, but the spin wave. If you want to see the magnon, there is also well-established technique like RIXS, RIXS, resonant inelastic X-ray scattering. And using that, you can see the magnon spectrum with very good resolution. But personally, I don't have an experience in RIXS. One of my colleagues is reviewed the RIXS streamline, so they're doing that a lot. The magnon, rather than the direct observation, the resonant inelastic scattering might be a good way for magnon.
Do you know how much the energy relationship can use it?
I don't know the number, but the to resolve the magnon spectrum, the energy resolution should be very good, right? But the RIXS streamline, yeah, they publish something for observation of the magnon, so I think the resolution might be enough to resolve the magnon.
Yeah, I'm just wondering if we can detect the magnon gap within few billion volt. Sorry, micron volt using X-ray technique.
Yeah, resolving magnon energy is still challenging, right? But there are some successful reports done by the RIXS streamline. Even in 400 light source, they set up the RIXS and they could observe magnon.
Udah
Yes.
Thank you very much.
But as you might know, there are some magnon in ferromagnet is relatively easy to observe. So magnon in antiferromagnet and magnon in ferrimagnet is very challenging. So that's an issue. But conventional magnon in ferromagnet is approachable from the RIXS streamline.
Okay, thank you very much. Is there any other question? It's not, then I think let's thanks Professor Kim. Okay, maybe I can call Adede to give to give some certificate of appreciation. Karen?
Satu, dua, saya lagi satu, dua.
Thank you very much, Prof. Kim, for the presentation. And again, just here of our presentation today, so let's all have a photo together with the presenter. Backgroundnya kita aja. Background ini. Okay, for the online audience, thank you very much for your attention, for your participation of this seminar, and please follow our YouTube channel and stay tuned for another series of weekly seminars and business. Ya, ada foto, foto. Ya, yang offline ini foto sama. Ya, belakang masih ada. Foto.
Enggak ada yang penting. Nah, satu, silakan semua. Satu, dua, sekali lagi, satu, dua.
Oke, terima kasih.
Setelah ini kita mau makan ya, kalau mahasiswa yang maksud silakan. Kalau pada sini kan mau ikut silakan. Makan siangnya mungkin di maksudnya ya di mau di tempat saya tempatnya itu oke. Kalau fiction itu ya buat ini ya. Nah ini oh bentuknya
Apa?
ya tidak apa. Hanya itu. Satu jam sama. Itu ini. Singkat. Nanti itu dari itu. Ya, itu sih. Saya kan juga dulu. Saya ketika ini dulu ya.
Dari sosial.
Pakai bau kalau kamu mau lanjut. Ini dari ini aja nih dari apa jadi adit bisa. Ya banyak